Okay, we're doing remote learning again, guys, and we really can't afford to not move on. So we're moving on. I'm going to share my screen in just a second. We are going to be, you guys did a video, or not a video, you did a virtual lab last time relating depth and pressure, and we're going to do derive some of those equations, and I'm going to talk about buoyant force and pressure and atmospheric pressure and stuff like that. And yes, I've got an assignment in the textbook, but I'm going to post it on Canvas so that you don't even have to find your textbook. Everything will be there. But I will definitely have something for you to do. I may change my mind. Who knows? We'll figure it out. But you definitely want to be watching this. So if you are watching this now and you know somebody who's not, give them a chat and tell them that they need to watch this. Okay? So I'm going to go ahead and kill my video because I'm going to write on the screen like I do in class. And you don't need to see my ceiling. And then I'm going to share my screen. I'm going to go ahead and do that now. Bada bing. We are gold. Nicely done. And here we are. Go us. So we're talking about pressure. And I know I'm doing this out of order from AP Classroom because I feel like this follows best next. Because we're going to be talking about pressure and fluids and all that fun stuff. Well, pressure, by definition, is force divided by area. Pressure is force divided by area. So in other words, if I'm exerting a force, we've been talking about exerting forces. We talked about it with work over a distance. We talked about exerting a force over time, and we called that impulse. Now we're talking about exerting a force over an area, and we call that pressure. And pressure is in newtons per meter squared. That's my unit. Or if you're going to be in your SI unit, it's called a Pascal. We don't use atmospheres in physics because atmospheres are a chemistry thing. We are using pascals. So we've got pressure is force divided by area. I am going to expect that you guys can do that calculation in your sleep. But it's something that this concept that we really want to understand. So let's talk about what happens if I'm in a fluid, something like this. And let's give me some light blue fluid here. Doesn't have to be water. It can be oil. It can be alcohol. It can be almost anything. And I've got an object here. Now, what forces are being exerted on this object? It's inside of a fluid. We're going to talk about air as a fluid as well. But so what forces are being exerted? Well, if we draw the free body diagram, I've got the force of gravity pulling on it. I've got pressure, the weight of the fluid. It's almost a normal force kind of thing, don't you think? So if I've got, and this is just a little blow up of what's inside my fluid. All this fluid is on top of my object, my little imaginary piece of something that's inside of the fluid. So it's as if there's a box sitting on it. So there's another weight on there. So there's a normal force. And I guess I'm going to call that the force of the fluid, not normal force, because lo and behold, there's a normal force from the surface to the fluid. Holy guacamole, Batman. That's a lot of forces here. So what we're going to do is, and somebody's saying, but wait a minute. So what about the sides here? Isn't the fluid exerting a force on the side? Well, this side is going to be equal to that side, and they're going to cancel out. And you guys have seen this before. If I drop a rock in a glass of water, the rock sinks. If I drop an ice cube in the glass of water, the ice cube floats, and you guys say, well, that's because the ice cube is less dense and therefore it floats. Why? What does being less dense have to do with anything? Well, density is mass per unit volume. We use this as a rho, and it stands for density. Lowercase Greek letter r. Density is mass per unit volume. Okay. So how much mass is being pushed onto this? Well, the first thing we want to know is that Archimedes' principle, this is the old story, I'm not sure how much of it is true, where Archimedes gets in the bathtub and he says, Eureka! Basically, he's saying that the volume displaced of a fluid is equal to the volume of the object. Equals the volume of the object. So that's not bad at all. Okay. Because this normal force here is going to get a special name. And that volume of the displaced fluid is now pushing not just up, not just making it, yeah, it's going to make it go up because it wants its space back. And so the buoyant force, see, there's my normal force, or my force of my fluid. The buoyant force is going to be equal to the mass of the displaced fluid times gravity. And this is called the buoyant force. And it comes straight from Archimedes' principle. Okay. Well, we're going to take a look at this. This is pretty much going to be my normal force. And going to kind of ignore that. It's actually this buoyant force is the combination of these two. And it's one giant buoyant force. Sometimes I guess it can point down and sometimes it will point up. It just is going to depend. Okay. And we're going to have net forces in here. Ooh, go us. So our buoyant force is the mass of the fluid. Well, the mass of anything, the mass is given as the density times the volume. And V here is volume. I'm trying to make it a capital V. And notice I'm not doing any of that cursive V or anything like that. It's just capital V. So there we go. Density times volume is equal to the mass. And so my buoyant force is the density of my fluid times the volume of the fluid times, well, the volume of the fluid is the same as the volume of the object because of Archimedes. Write this down. It is on your equation sheet, but it is also definitely card worthy. So there's your buoyant force. Okay. Now we're going to kind of get to the stuff that you guys worked on last class. And, you know, the whole lab thing. And so the depth here. Well, shoot. So this is my buoyant force. And an object that floats, so let's talk about floating, sinking, or rising. Okay, something that sinks. Well, that means that the force of gravity is greater than the buoyant force. So the mass of the object times gravity, and that O is not a zero this time, is greater than the mass of the fluid times gravity. Hey, and notice my gravities cancel. Okay. And the mass of the object is the density of the object times the volume. The density of the fluid times the volume. The volumes cancel. And so the density of the object is greater than the density of the fluid. Therefore, it sinks. You guys did that as an experiment in what, 6th grade? Now we've proven it mathematically. Something that's rising, that means if I push it down, it comes back up like a beach ball. You try and shove the beach ball underwater and you let go and it shoots up into the air, and we could actually determine the speed and the maximum height of the beach ball. Yep, you know where we're going. And so an object that's rising says that the force of gravity on the object, the weight of the object, is less than the weight of the fluid that has displaced it. And it's the same math. I'm going to assume you guys paid attention. And so the density of the object is less than the density of the fluid, and it bobs up to the top. Okay. Something that just floats. That means if you put it there, it stays there. Floating is not the same thing as rising, because we're going to be looking at floating and stuff like that. I'm not going to go into as much detail today because it is remote learning, and we were told to keep it short. So I'm going to keep it short. So my floating says that the force of gravity is equal to the buoyant force, and therefore the density of the object is equal to the density of the fluid. That's it. That's all we got. That's not too bad, is it? So this is buoyant forces. There is a lot more to buoyant forces, but today is the overview, just an overview, okay? Not a big deal. We're just looking at an overview. So let's look at that free body diagram. I've got my little object in here. Okay. I want to know the net weight. So I want to know the apparent weight of my object. Let's change it from weight to mass because I don't like weight. Apparent mass of the object. If I weigh it underwater, it weighs less. I think we've all known that. If you weigh something, because the water is pushing up on you. It's kind of like being on an inclined plane. It's going to weigh less. So what's the apparent mass? Well, let's draw a free body diagram. We know that we have the force of gravity. We have, well, lo and behold, now we have the buoyant force. And then we have the net force, which is our third picture here. Our net force. Which way is it going to go? So I'm just going to put it down here. Because if you draw it upward, you'll get a knot. But so let's do our net force because we would want that to be 0. So our net force is going to be the force of gravity minus the buoyant force. Okay. And so that's going to be the mass of the object times gravity minus the mass of the fluid times gravity. And the mass of the object is just, we could do it as the density of the object if we wanted. We're going to need that anyway. Let me go ahead and fix that. Woof. So this is going to be the density of the object times volume times gravity minus the density of the fluid times volume times gravity. And there's my net weight, my net force. And notice that I'm going to have a difference here. My apparent weight is the density of the object minus the density of the fluid times volume times gravity. Well, if I want the mass, I'm going to divide gravity out. So the mass net is just the density of the object minus the density of the fluid times volume. Here's your little trick. We already looked at this. If the density of the object is greater, it sinks, it goes down. If the density of the object is less, hey, I get negative mass. It's going up. And if the density is equal, it says I have zero mass. Yeah. The net mass is zero. Well, this is actually kind of useful because I don't always know some certain things. And the density, if I want to know the density of an object, some objects are not easy to measure their density because you need their volume and you need their mass. Yeah, it's kind of crazy. So this is actually not a bad way to do things. Okay. So this is actually how they will do BMIs, your body mass index, to determine your percentage of fat to muscle to everything else, because we know what if we can measure your density, then we can make approximations, and it's always an approximation. And so that's how they will measure your BMI. Sometimes they'll tell you they can do it without the water test. They can't. That's just an approximation. If you really want to know your BMI, you got to do the water test. Okay. So we've done all right. Okay. We've done okay with buoyancy. And so I'm going to work a couple problems here. I'm going to grab a couple out of the textbook just because I can. And while I'm doing that, I'm going to go ahead and pause my recording so that you're not listening to me just try and find something. Give me 1 sec. Okay, and we're back. I found the problem I wanted to do. And so, like I said, I'm not going to keep this very long because we were told to keep it short. The spherical balloon has a radius of 7.15 meters and is filled with helium. And we want to lift the cargo, assuming that the skin and structure of the balloon have a mass of 930 kilograms. Neglect the buoyant force on the cargo volume itself. So what I've got here is a helium balloon, and it's got a box, and I've got stuff inside the box. I want to know how much stuff can I put in the box to have it just lift. Not lift at an acceleration, but just lift. So we're going to write down what we know, and we're going to look at all of our forces. Since it's just lifting, we know that our net force is going to be equal to 0, just lift. And therefore, our buoyant force is going to equal the gravitational force. So that's our starting point. That's where we need to be. Then we're going to go and look up the density of helium, which is I just closed it up, 0.166 kilograms per cubic meter. And the density of air, which is 1.2 kilograms per cubic meter. I looked them up while I had it paused. And so now I've got other stuff I've got to figure out. For one thing, I need to figure out the volume I got to figure out, I don't have the volume. All I've got is the radius. So now we're back to geometry, and I know that the volume of a sphere is 4/3 pi r cubed. Okay. I know that the mass of my object is going to be the mass of the balloon plus the mass of the cargo. Okay, here we go. So 4/3 pi r cubed. So that's 4/3 pi times 7.15 cubed. I'm getting out my calculator here. So 4 pi times 7.15 cubed divided by 3. And I get 1,531.11 cubic meters. If you put that on Desmos, you can see 4/3 7.15 cubed. I got slightly different if I use 3.14 instead of the pi button, but we're all good. The mass of the balloon, so that's going to be 930 plus the mass of my cargo. And the mass of my cargo, I'm going to put a box around it because that's what I'm looking for. Okay, so let's do this. What mass of the cargo am I going to need? So I know that the density of the fluid, in this case, the fluid is air times volume times gravity. It's on the outside of my object. Density of the object, and this is going to be a little tricky, times volume times gravity. Gravities are going to cancel out. Isn't that cool? And we don't have a volume of the cargo. We're just assuming neglect the buoyant force on the car. So in other words, I'm not going to have an extra volume of cargo. It's all included in that 750 in that one volume. Okay. So here we go. And the volume is the same. Okay. So I need the density because I want to know the mass. Okay. So the density of my object has to equal 0.166. Actually, the density of my object has to equal 1.2. So this is going to be 1.2. My volumes cancel, bam, bam. I calculated that out for nothing. Oh, wait, I didn't do that. Okay. I knew there was something crazy here. Okay, well, let's just go ahead and figure this out here because there's more to it. I'm just being a goofball here. Okay. So the mass of that's equal to, and the density of my air times the volume, or the density of my helium times the volume, that's kind of different than the cargo because that's not included in here. And so 1.2, there's the density of my air times my volume, 1531.11 is going to give me, the gravity still cancel, 1.2 times 153, 0.11. Okay. And I get a mass of 1,837.332 kilograms. That's the mass of the air that I displaced by that spherical balloon. We are neglecting the cargo. So that's got to be the mass of my helium plus the mass of the cargo. And the mass of the cargo plus the balloon This is going to be 930 kilograms. This is 1837.332. And that's going to give me the mass of the helium. Well, the mass of my helium plus mass of cargo. Forgot the variable. Okay, so let's recap where we got here, how we got here. Here is the mass of the fluid, and it's just the density of the fluid times the volume. We are neglecting any volume taken up by the cargo, and we're only including the volume of the sphere for the purposes of the air. That's the buoyant force. So I'm not worried about that. So I calculated the volume of the air, and I have the mass of the air. So I'm going to write that right here. This is the mass of the air. Now, the balloon itself, its mass is going to be the mass of the helium inside this balloon, plus the mass of the balloon itself, which is part of what I'm trying to figure out. So this is the density of helium times the volume. This is the balloon itself. And this is the extra cargo. Does it kind of just feel like a Unit 4 problem where we're just doing forces? Kind of. Okay. So the mass of the helium is the density of the helium. So let's go ahead. I'm going to do a side quest here. Is the density of helium times the volume. The density of the helium is 0.166 times the volume, 1531.11. Grabbing out my handy dandy calculator. Times 0.166, and I get 254 kilograms. Never thought helium would be that heavy, did you? So I'm going to have 1837. I'm going to go ahead and just, let's go ahead and keep my digits. 332. In class, I would have dropped the extra digits a long time ago. 254 plus 930 plus the mass of my cargo. Now this is something you can work with. So I'm going to take my 1837, subtract off my 254, subtract off my 930, and I get a mass of the cargo of 653 kilograms. There you go. That's how much mass it can lift. Okay. So now you've seen the video. And like I said, I'm going to go ahead and keep it kind of short. I know it's not, you didn't think that was short, but it's short for a class. And I'm going to assign a few problems. They're not going to be super long. They're not going to be super difficult, but they should keep you at least engaged until we get back to class. And it might be a minute. So I will keep these coming, and we're just going to cross every bridge as it falls. Okay, guys? No big worries. Don't worry about things you cannot control. Okay? So I will see you later. Don't forget to complete the assignment. That's your attendance. And if you have questions, my office hour, I decided to do 11 to 12 so that you guys could sleep in. Also, everybody else wanted to do 9 to 10 to get it over with. I'll do 11 to 12. That way you guys you have a chance to actually ask more questions. All right. I will see you guys later. Have a great evening and great day. And I will talk to you when you get to school.